everyone. My name is Mona Belid, and I will be the moderator of the next talks on stage two. So, the next talk is entitled Streamlining a Data Process Using Shiny and AWS. So, it will be presented by Eleanor Mer. So, she's a data scientist at DataRock with a background in geoscience, particularly geochemistry and macroanalysis. So she completed a Bachelor of Science with honors at Monash University and PhD in geoscience at the Australian National University. So after a few years as a postdoctoral research fellow at the University of St Andrews in Scotland, she converted from academia into industry by returning to Australia for her current role with DataRock. Thank you very much for being here. The stage is yours.
Thank you. I'd like to share with you today a story about a project that my team and I have recently finished. It was a really quite big project and a challenging one. So at DataRock, we provide machine learning and data science solutions for the mining sector. And in this project, we helped a client streamline a data process. We got them from a really tedious manual process to a fast, automated, robust, and scalable one by leveraging the power of Shiny, Python, R, and AWS. And although I can't share with you the specifics of the subject matter, I can share some interesting things that we learned along the way by way of an analogy. So I want to start by explaining the problem that our client had. Our client was a team of fruit salad experts in a large company, and over a number of years, they developed this really good data analysis method. It was called the fruit salad evaluation method, and it was providing a lot of value to their business. Basically, they would receive photos of fruit salads, and they would evaluate them based on asking questions like, how many blueberries are in this salad? What proportion of the salad is orange or yellow? And by answering these questions and looking at visually at the images of the fruit, they could evaluate each salad and rank them for their revenue potential. So this process was providing such good value that the demand for their work kept increasing from other parts of the business. The problem was that the data process they had was quite slow and tedious. They would receive photos of the fruit salads, store them on a computer in the office. They would have to use two different pieces of software to extract the statistics of the fruit that they needed. And they would copy and paste data from those two bits of software into a massive Excel spreadsheet. And then by flicking back and forth between the software and the Excel, they could look at all the data and the images and make their evaluations. So this process worked, but it couldn't scale. It could take them weeks to go from getting the images of the fruit to providing the evaluations to the other parts of the business. And so to keep up with the demand for their work, they wanted to streamline this process. They imagined that it would be possible to go from getting the fruit images and automatically extracting the statistics, so they weren't having to do a lot of manual copying and pasting anymore. And they envisioned a web app that could connect to the data so that everything that they needed would be in one place. And here I have to give a huge amount of credit to the client's team. This was a team of fruit salad experts, not software engineers, but they produced extremely detailed and well thought out requirements for how the data pipeline and the app needed, like what it needed to do. And they produced these beautiful mock-ups of how the app could look. So that's where we started from. And this is how the project kind of progressed. Initially, we started by proving the concept, trying to get the minimum functionality in an app connected to a data pipeline in the cloud. And then very quickly, we needed to address some speed and stability issues. Once that was done, we had to do some custom image display to really meet the needs of our client. And so for the rest of this talk, I'm going to go through those 3 phases and talk a little bit about the things we learned at each stage. So to start with, here's how we set up the proof of concept data pipeline and connected everything together. We would receive images of the fruit salads and place them in an AWS S3 bucket, which is this cloud storage. When the fruit salad picture hit the bucket, it would trigger a function to run on an AWS Lambda. And this is just like a Python function that would extract some tabular data from those images. The tabular data was stored in another S3 bucket. Shiny needed to connect to both the images and to the tabular data. So for the images, it just went and grabbed the images directly from S3. For the tabular data, we used a service called AWS Athena, which allows you to query over multiple files in an S3 bucket as if they were already in a database, so we can use SQL to do those queries. The Shiny app was deployed on a POSIT Connect server, which the client already had. So data engineers in the client side got all the deployment working. That was nice in that we didn't have to worry about it, but the flip side was that we weren't given access to the server for privacy reasons, which meant that we couldn't actually test the app in its live environment, which caused issues throughout the project, which I'll touch on later. And then you'll notice a little Python symbol in the corner there. We made a decision pretty early on to use Python together with R in this Shiny project. And I wanted to mention a couple of things about that, our experience with that. So this project started at a time when Shiny for Python wasn't mature enough to use for a project of this scale. But we still made the decision to use Python together with R pretty early because we had some Python code already. So from some of the earlier stages of the project, we had some functions that did some things with the data that were useful we needed in the app, and I didn't want to need to rewrite those functions into R. But along the way, we kept finding reasons it was handy to have Python packages available. Pandas was one that was really useful because it supports multi-level indexing in a way that Tibble and data frame in R don't. And so that was actually one of the requirements that the client had, was to be able to export tables in a particular format that Pandas handled really easily. We also used NumPy and Boto3, and I'll touch on those a bit later. There were, of course, challenges with using Python and R together. One was debugging is harder because you can't step through the Python functions when you're debugging. The other one, which I never actually quite got to the bottom of, was caching. As far as I could tell, the caching functions in R can't handle Python objects. So I suspect the solution to that is probably to implement caching in the Python package itself. But if anyone listening has encountered this and come up with solutions, I'd be really interested to hear about it because we never quite got time to figure that one out. So once we'd got R and Python talking to each other and the app talking to AWS and the app showing statistics and images and deployed on the client's tenancy in its live environment, we were feeling pretty happy with ourselves. We had a working proof of concept and I got ready to go on holiday. But as I mentioned, we couldn't test the performance of the app in its live environment because we didn't have access. And so within a couple of hours, we got some feedback from the client. They said, when we try to load too many fruit statistics, the app is actually crashing. And they also said that the fruit salad images are taking a long time to load. Is there anything we can do about that? So we started phase 2 of this project, which was addressing those speed and stability issues. So we went back to our new data process and looked at where the inefficiencies were. And actually, there were 2 places where we had inefficiencies, but both were kind of the same thing. the key thing was we were trying to bring too much data from AWS to the server where Shiny was running. It was just a large volume of data, and it was taking a while to transfer. And sometimes it was so much data that the server was running out of RAM, and that would crash the app. So here's how we address those two issues. The first one, in terms of bringing the images to the server, we added some more pre-processing to the data pipeline. So we chopped up the fruit salad images into little pieces of fruit, and we stored those little tiny images in NumPy compressed arrays. Another reason it was handy to have Python. For the tabular data, we needed to make better use of SQL. So the route we had chosen in the beginning was to just bring in a whole bunch of data from Athena and then use R's really nice paradigms for wrangling data, dplyr functions and so on, to aggregate that data into a form that we needed to show in the app. So we needed to do that aggregation in SQL instead, so that we didn't have to bring such a large volume of data into the app. But initially when I tried to do this, it seemed really hard because the SQL queries were extremely verbose, long, slow to run as well. And so we did 4 things to address this issue. One was we changed the schema of one of the tables from wide to long. That made the SQL queries a little less intuitive to me, but also less verbose. We partitioned the database, which meant that each query didn't have to scan as much data. We stored the tabular data in Parquet files instead of CSV, which meant just also a smaller volume of data that had to be passed through by Athena. And the fourth one is actually the most critical here, which is that we were able to get Athena to run multiple queries in parallel. We used the Python's Boto3 library for this, mostly because the team already had, we were already familiar with Boto3 functions. I think there is an equivalent package in R that could do this though. And this was really good because it meant that we could split these long verbose queries up into manageable chunks and speed them up by running them in parallel. Athena handled all of the parallelization. Okay, so once we had dealt with that, we'd implemented those changes. We still had an app that was basically the same as at the end of the last stage, but it was now fast enough and it was stable. So that was great, but we still needed to do some work, particularly on the images. So this is part 3. As I mentioned, our client had very detailed requirements for how this app needed to work. And the requirements for the images were that they needed to see the images in a grid. Each image needed a scale bar. They needed to be able to zoom in and out. And critically, they needed to be able to see the color of the image in a tooltip as they hovered over the image with their mouse. So Plotly seemed like a natural choice because it has pretty much all of this functionality built in. Subplots for a grid, zooming and tooltips are handled natively, and we could kind of use the axes tick marks to be like a scale bar. But we quickly ran up against the limits of Plotly. What we found is that when we were rendering large images, Plotly was rendering them really slowly. And it seemed to be because each pixel in these large images was kind of treated as an individual little data point, which is a lot of data for the browser to handle. And this is made worse by the tooltips, because the way Plotly does tooltips is passing another layer of information about the same size as the image to the browser. So, and the other issue was actually some of the layout of the grid. Sometimes one of the subplots would just decide to be a little bit smaller than the others, and I was never quite sure why, but it was a bit of a problem when we were trying to show images on the same scale. So to get around these problems, we actually ended up implementing a custom solution using HTML, CSS, and JavaScript. I'd never really written in these languages before, so it was quite a learning curve for me, but it was really I found it really amazing to see how much flexibility there is in Shiny if you know a little bit of these languages. So the way we implemented this was to render the images on HTML canvas tags, which exposes the RGB value so that JavaScript can see it. So then you can use JavaScript to create the tooltips. And we could use JavaScript also for the scale bar and to implement a simple zooming functionality, which is basically just redrawing the image at a different scale. So once we'd integrated that new fancy image display into our app, that was pretty much the main last challenge to overcome. And we came up with this app that met the needs of our client. So one more slide just to talk a bit about the impact of this project. This is actually one of the more impactful apps we've built. It's made a big difference to our client in terms of speeding up their workflow. We had a really nice conversation with the manager of the client's team recently, where he said that he'd looked over towards his team and seen 3 of them all using the fruit salad evaluator tool to do their daily work. So it's really made a difference to how much value they can provide to their business. It also sets up, implementing this data process sets them up for improving their fruit salad evaluation method in the future, potentially by bringing in more advanced computer vision techniques as well. So yeah, pretty much the key point here is that the success of this project was down to the power and flexibility of using all of these different tools, R, Shiny, Python, and AWS. And of course, all the people involved. So my colleagues, Dave, Ryan, Mark, Masa, Yasin, Tom, and Pep all contributed in various ways to this project. And on the client side, I unfortunately can't name any of them, but there were several extremely dedicated people, including the data engineers who helped us set up the infrastructure, and of course, the fruit salad experts. So that's it. Thanks for listening.
Thank you so much. It's really very interesting. I loved how you managed to integrate many tools in one project. Yeah, thank you for so much for sharing this with the community. Let's take some questions. So from the chat, so we have a question from Sarah. Is there a reason that in your example, that was the mandarin and kiwi fruit columns are whole numbers, but the others are not?
Good question. Where here? No, that's just me being a bit lazy with producing some random numbers to put in a table. Yeah, it doesn't really reflect the structure of the real data. But thank you for asking.
Fine. You have a second question from Marcin. So how do you approach managing CSS and JavaScript code alongside regular Shiny code, like embedded in R files, separate files, and somehow loaded?
Yeah, thank you. Good question. So I understand there's quite a few different ways to do this in Shiny. We ended up with quite a bit of JavaScript code. So we had separate JavaScript files, and same with the CSS. The HTML was using R's HTML, like Shiny HTML functions. And that was implemented by kind of creating, using those functions in like an lapply to create an arbitrary length of grid, and in a render UI widget. Yeah.
Great. Thank you very much.